purpose of today's session is going to be model development production case study. Part one, that's our title. So what we're going to be looking at here is developing a model and getting to that optimization stage. So we're kind of going that full scale data science style project where we need to kind of import some data, work with it, do some cleaning, and get into that modeling stage, as well as, again, the goal is going to be that you can all walk away with the ability to then perform a grid search and then optimize your model. So kind of understanding like the full scale aspect of this project. So our goals for this session specifically, we're going to use Jupyter Notebook to explore the Diamond Seaborn dataset. I highly recommend, if you haven't ever played around with any of the Seaborn data, it's a great place to pull data from. And there's certain ones of them that are kind of set up, like the one we'll work with today, where it has that full scale capability. If you've worked with like the Titanic, there's a million tutorials out there for like Titanic data and Iris data. And don't get me wrong, they're really cool for like getting the idea behind it. However, if you're looking for something where you can practice some of your data cleaning, Diamonds is a bit cooler. So first thing here, we're going to bring the data in, we're going to do our exploration, and we're going to see that it needs cleaning. So we're going to go through some common techniques on how to clean and some of the thought behind that. We'll create visualizations in order to better understand our data. So I love to use like certain templates I've created over the years, and like I'm going to give a few of them out with you guys today of like, these are copy and pastable, some slight edits. And that's kind of, again, of the goal of these live sessions is you're building up a repository of code that you can make slight adjustments to and use on any data set out there. So we'll see some different ways to visualize both our categorical and quantitative data. Then we're gonna go ahead and split into training versus testing groups. So we did that a little informally in last week's, where we just did kind of like the 80-20 split, but there was no like kind of algorithmic way of doing it. And this week we'll see kind of the more formalized way that, like I would, as you could say, industry standard. Like if I was doing this for a client, this would be the way in which I would do my splitting. It wouldn't be that kind of ad hoc method. Then we'll go ahead and train and test multiple regression methods. So we'll look at a bunch of different ways to get to it. And then a lot of times here, people get stuck on the models themselves, but what we're really worried is about the statistical way we're measuring that success. So when it comes to regression, we don't necessarily have an accuracy score. Now, there's ways we can kind of ascertain how accurate they are. I showed you guys, I think, last week, and the day one, a way of looking at absolute value distance, like predicted versus actual. That's one kind of way that I suggest exploring your data, maybe looking for like where those trends may be of having issues. We did that with our first lesson together. However, I'm going to look at R squared again today. I know we talked a little bit about that last week, but we're going to kind of see more of how we can work with that R squared today to evaluate some different models here. Then we'll use cross-validation to optimize it. So we're going to cross-validate and then use what's called a grid search. So the grid search is going to be the extension at the end. That's something you guys are going to finish up on your own time. The only reason being is that it's really dependent on how much, what kind of device you're running and how long it may take to execute. I've run it on some of my devices and it takes, a minute. I've run it on some of the other ones I've had in the past, and it might take 10 minutes just to, run this on a little block of code. But it's a cool thing that I want you to have that experience with and kind of seeing how to truly optimize a model. All right, so this will be where I'm going to do a little just dump of code. So I'm going to use Jupyter just because I want to make sure everyone's looks like mine, and the coloring's the same there. So like for those keywords turning green or blue, whatever it may be. What I'm sharing over the code in is just something you could also check out. It's a collab notebook through Google. So that's just going to be a nice little shareable link. So any code that you see on my screen, I'm also going to dump in there. So it should be a little bit of a delay until it updates. But with that, so if you have a typo, so I always suggest everyone, you should try typing in your code yourself first. It's just good practice and it kind of gets you that good muscle memory type thing. However, for some things like our list of imports that I'm going to put on screen right now, I just threw those into the Google Colab file as well, just because typing in imports is fun as it is. It's also not like a super important skill set to have. All right, so kind of our big 4 imports. So anytime I do anything in the world of data, I am bringing in these 4 here. We've seen in the last one where we use just pyplot as pyplot. So a big 4 here, NumPy, Pandas, Seaborn, and then Matplotlib. We've seen in the previous lesson where we just used pyplot directly. This is kind of the Pythonic preferred method here, so importing as PLT. The reason why I really want you to get used to those types of statements is just because, again, like as data scientists, you're often going to be working on Google, and you're going to be going through Stack Overflow and looking at other people's examples of how to create more optimized models or learn new things. And getting good at those the kind of the typical practice things like knowing that what PLT means, that it's referencing this module here. That's kind of a useful skill just to make it easier for you to understand new code. The one we'll also be using here from scikit-learn model selection is going to be train test split. You'll see this one a ton too in any type of work you're on. So this would be like one of the industry standard, like more, I guess you could say it randomizes the selection a lot more than we did with that 80-20 little shortcut we had the other week. So this will be kind of the way we see that going forward. Here, we brought in a couple of different error metrics, so mean absolute error and mean squared error, as well as our R squared. So if you remember this one here, let me go ahead and get that open for you. Learn options. So this is something you definitely might want to bookmark. So this is our metrics for scoring, and it's the scikit-learn like official page for it. So on this page here, we have, we'll see some different options there. Clustering, and then in regression today. So here we can kind of see all the different options. Probably your most common is going to be R squared, but again, the more precise you're getting, depending on your usage case, some of these other ones might come in handy. And if you ever need more thing, you just click on it. Pretty cool. They give you a little more information there. So definitely a bookmark. That's the last one I just sent in the chat. You want to keep handy and have it saved somewhere, just as a good way to reference it. All right, going on down here, we're just pulling in linear regression, and then we have some polynomial features. Here's some other regressor options as well. In no specific order, but that's kind of where they're coming from. And then we have our stats models, just a shortcut to that if we decide to use it. All right, so let's go ahead and get some data brought in here. So I'm gonna go ahead and just say DF. Now, if I had a bunch of different data frames, I typically name this one as DF diamonds. However, since we're only gonna be working with one, I'm just gonna call it DF. So if we're pulling it from Seaborn, I'm gonna say sns.load underscore data set. And then it is just called diamonds. And then let's go ahead here and we're gonna go ahead and take a look at this. So we're just gonna say df.head. I'll go ahead and pull 5, which is the default. I always like to just put the number I want, I guess. So let's go ahead and check this out. So some things we have in here, we have the caret of the diamond, a cut of the diamond, color, clarity, depth, the table of the diamond, the price, and then an X, Y, Z variable. Now, chances are that unless you're like a diamond expert, you don't know what these things are. So the first thing I suggest is, even if you're working through a tutorial, you always want to make sure that you kind of know what the data that you're working with is. Kind of nifty thing here, explaining our code. Where are we at? It's not liking the way I'm doing that. So let's just do this. So we'll talk through these, and I did share these as well over in this shared file, so you can see them there, just to avoid taking the time to necessarily type these notes in. So while we're getting these things here, I'm just commenting out just so they could be the text as opposed to being seen as code or markdown. And again, I'm including this all in that shared file as well. So these different measures on here. So what we're looking at here, caret is the weight of the diamond, equivalent to 200 milligrams. So this will be a good indicator here, our caret. Hopefully that gives us an idea of what we want to predict later on. Quality of the cut. So it's saying ideal, premium, good. So we don't even know the options again here because we're only looking at the first 5 rows. The color. So this is how diamonds are graded from J to D. So it does tell us here, this is, it's got some order to it here. The clarity, and it shows us how to interpret that as well. Depth, table, price, and then here are X, Y, Z, so the dimensions of the diamond. So that's one thing I would suggest is when you're getting to a data set, if you don't know what some of the data is, that would be something you definitely want to research. So for me, it's whenever I work with like medical data or school data. Those are two professions that love acronyms. So if I'm working on a medical data file and I'm looking at these different columns and I don't know what they mean, that's the first thing I'm going to do is reach back to a client and be like, hey, look, like I'm great with numbers, but I don't even know what these variables are, so I don't know if they're important. I don't know how to interpret them. Same thing with like the acronym side to it. Like here, these are named pretty clearly, but if these were just like random letters and names like the XYZ, for example, without knowing that it's representing the dimension of the diamond, like that'd be something you'd really want to reach out on. And again, this is why I like Jupyter or the Google version there. Either way works the same essentially as that interactive notebook, because I'm someone who likes to take really good notes. So even my personal projects, you'll often see notes like this in here, like walking me through like, okay, like, hey, like remember the fifth column represents this, or here's what this variable dub is, just so that, again, I'm not trying to learn the same thing 10 times. Keeping good notes for yourself is just a great practice that way. All right, let's go ahead and check out what else we have. So let's see what kind of variables these are. So if I want to go ahead and say df.info. So we talked last week, there's other ways to kind of summarize this. We could do dtypes. I like .info just because it really gives me an idea here of like what is in here. So we can see if we have any null values, so any missing data altogether. I can also see here the different options here. So we have our categories for those. And then our float 64, our ints here for price. So the thing we're going to be trying to predict today is going to be price, because that would be kind of the goal here, right? We want to know how much we could sell a diamond for. So if we're making a business plan, I'd want to be able to gather data and predict like, okay, so if I get in a diamond with these characteristics, what can I sell it for? All right, so again here, if we had any nulls, we've seen that dot is null in some, that kind of more rudimentary method. But again, this is kind of my go-to way. I like to use just .info there. All right, let's see if we can kind of visualize what this is going to look like here. So maybe get some descriptors here. So if we do .describe, this is kind of the shorthand way of getting your mean, median, mode, like your 5-number summary here, mean and standard deviation, as well as a count. So we can see is again because we have no null values, the counts are all exactly the same. So that's another way to kind of look for if you have any nulls, is to do a describe and look at the counts. Here it gives me my means across the board, standard deviations, so we can kind of tell here what might be a beneficial predictor. So what you're looking for is a large disparity between mean and standard deviation. So if we think about a multiplier, so the kind of more spread out those are, the more, I guess you could say, easy it is to predict within that data. So for example here, if I'm looking at price is going to be pretty challenging to predict, right? Because we look here and it's okay, well, my mean and my standard deviation are almost the same number. In fact, standard deviation is a little higher. So predicting could be challenging, but we can kind of see which one of our models is going to do the best there. If we're looking at table and depth, we see those are huge differences, whereas caret, mean still higher, like respectively, it's a little less than double, so like should be usable. And then same thing, our X, Y's, and Z's here have good multipliers, like the scalar value. So standard deviation times something being equal to the mean. It's not an exact science, but it's a good like kind of a shorthand way to kind of pick out some good variables there. Now you'll notice when we do .describe, it automatically ignores anything that's a categorical value. So we just see cut, color, and clarity weren't even considered in this. So that's a good way of looking at it there. All right, now let's go ahead and build in some variable distributions here. So when I say distributions, now that we've kind of got the summary statistics of them, we want to go ahead and visualize these to see what they look like. So I'm going to go ahead and type for a second here, and then I'll talk you through the code. So for this one, this is just setting color codes. So it's saying that I'm going to go ahead and use a specific set here that I want to use. And then I'm going to name my colors. So from a color palette, I choose bright. Now there's a ton of different ways you can kind of name or define what color pattern you want and like the specific order. I love Seaborn's palette just because it saves me, 10 lines of code. And like truthfully, unless your company is going to pay you extra to use like their, theme of colors, I would say that when it comes to coloring things, you can either use default options. I like a little bit of specification just because, sometimes like I want to make things the same color. So maybe two variables go together. So I make them both red or both blue, just so that those kind of, I could highlight those relationships. But as far as like customizing the colors of my graphs go, this is about as extensive as I've ever needed to get. So with these two combined lines of code here, you can actually, if you want to maybe put it here, just so it's kind of closer together. That's always a cool option. And then these are just my notes on this. So one nifty little feature in here is like the deep, dark, bright, whatever maybe. I like bright because it shows up pretty well on my screen. However, if you have clients or who are colorblind, there is a specified set for that, which is kind of a nice feature there. So that's just kind of specifying which one I want to use. You could play around, like once we run this block of code, you can just swap out this keyword here with any of these, and you can see the other options. So this is going to give us our 2 rows and 4 columns here. So this is something you'll see in a lot of, I guess, tutorials, but it's one of those things I feel like is never really well explained. So this is that kind of cool copy and pastable code that I'm going to do my best here to make sure that we all understand really well by the end. So when we want to create a subplot, so we want to create one big plot with multiple little like kind of grids on it for our graphs. This is one of those kind of more friendly ways of doing this, only because then we could look at everything at once, as opposed to, creating 10 different, 8 different, 5 different graphs. We can kind of do it all at once here. So this is the general argument. So, fig, axis. So fig is a shorthand for figure. And then axis, when we define this, it'll be PLT, which references that matplotlib.plt. And I did put what we have so far into that shared file as well there on Google Colab. So what I'm going to ask is, if you don't have this, go ahead and copy and paste that. And then I want you to work through kind of some nifty shortcuts here. I'm going to have you help learn how to write out like I want you to really get the command. So this is going to be the only part I really copy and paste there. So when we do that subplots command, the 2, 4, so the first thing is the number of rows. So the number of horizontal kind of lines there, and then the columns, so our vertical splits. And that gives us 2 times 4. So we have 8 total plots. Something that's nice with this way too, is if you ever have too many plots, like that's okay. You don't necessarily need to have, like for example here, we might only, I think we're only using 7 of these, right? Yeah, let's see, 1, 2, 3, 4, 5, 6, 7. Yeah, so we're only going to use 7. So one's going to be blank, and that's cool. Doesn't really make a difference. All right, so at this point, again, this is what you want copied right now. All right, so with coding, the more you get used to it, there's a good common practice of when you're going to do something a bunch, you want to think about ways to save yourself the time, such that you don't want to have to, type more than you have to, I guess you could say. So work smarter, not harder. In this case, when we're using hisplot, what we're going to see in here, and also just a bit of notation advice here. If you go and look up a lot of tutorials, an old version of Seaborn use displot, so a D instead of an H, or DIS plot without the T. This is the most recent one. So if you're ever going through a tutorial and it's like, this is going to be deprecated, this doesn't exist, it'll suggest you change it to this. So in this case here, what we're looking at is we need to define where it's coming from. So where our data is at, which is going to be from our data frame. And we want to reference just a column here. We could use the specific index of it. I prefer to use names, only because then I know exactly what I'm talking about. I don't have to be like, oh, it's column 0. Let me go see what column 0 or 2 is. The colors here, this is our argument. We could actually specify a color. And then this AX is equal to axis. We're going to use this to name it, so where it's from. Now, I'm telling you, we're going to have 7 plots. So what I'm going to say right now is highlight just this line, copy it, and then let's go ahead and paste that thing 7 times. 2, 3, 4, 5, 6. Well, I guess you're pasting it 6 times. So that's kind of a shorthand way. once you realize you're going to use something a bunch of times, if you can kind of skeleton it, it helps you avoid errors too. There's nothing worse than when you're, getting error statements. It's like you forgot a comma somewhere. So once you get a nice skeleton, using it over and over again is pretty beneficial there. All right, so first thing, while it's all nice and vertically symmetric, let's look at our color options here. So I'm gonna go ahead and just start throwing some in. We can use 0, 1, 2, 3, 4, 5, and 6. So all this is doing is it's just kind of using that default color order, and it's avoiding me, repeating a color or having the same thing show up twice. And if you do search up like this specific package, it can show you all the different color options there. So let me go ahead and show you guys where that's at. So if you guys check out in the chat, here's that Seaborn page where it talks about the different color palettes. So this kind of goes through some different ideas on when or how to use them. So for example, if we're working like a heat map, you may pick a neutral color to a blue or green, red, whatever it may be. I'm talking about different hues, so with different kind of subplots in here. And like this one, talking about the overall usefulness between the two. So if you want to check that out, this is some cool things to look back on. And here are the palettes that I'm referencing here. So I prefer bright. It gives me a ton of saturation and a ton of luminance, just so that it really kind of makes those graphs pop. And then colorblind is kind of designed to show that grayscale in between. So a lot of different color options here that you can look through if you want to experiment more with that. All right, so from this, what we're gonna do now, we got our colors. Let's go ahead and pick where things go. So if I want to think about this grid and I think about a rectangle, so what this is gonna kind of look like here is, let me think of a good way to help you guys visualize this. So if we think about this, now obviously it'll be much more kind of nice looking than my Word document table here, but this is going to be kind of the visual of how we can name things. So the first row here is actually just indexed, like I forget, everything else in Python is row 0. And then the first column here is also column 0. So this spot here is represented by 0, 0. Then we go to 0, 1, 0, 2, 0, 3. This one is going to be 1, 0. And a common error is when you don't necessarily understand how to name these things. That's a huge error I see a lot with students, where it's like their error is coming from like they referenced a cell that didn't exist. So like they're calling this row 1 and this row 2. So then this would be 1, 1, 1, 2, and 1, 3. So that's kind of what ours is going to look like. Obviously, though, it'll look much more like, nicely grid shaped once we print it out. So for our first one here, we'll just kind of go in order. I'm gonna go ahead and say 0, 0. And then I'm just gonna put this one to that one to the right. And again, there's no necessary order here because we don't know what it's gonna look like. But however, we might wanna change some things up just to improve our visualization here. So then I got 1, 0, 1, 1, and 1, 2. So when I first make a visual, I just kind of go in order. So like, I'm just gonna copy and paste some stuff from up here. That's kind of just a default ordering. So top left all the way down to the right, and then bottom left over to the right. Now, when we're naming these things, so I'm just going to go in the order they are up here, just because that's the easiest way. Now, sometimes you have some really complex column names. So I'm going to go ahead and put a little cell up here. And what I'm going to just say is df.columns. And this is also a great way is if you're ever going to be, trying to copy and paste data frames, that .columns thing is a nice little shortcut because you can copy and paste directly from it. Like you can from here, but I don't like doing that only because this is more like visual. Whereas here, it's just, kind of that raw text, so it's easy to copy and paste from. So you'll notice when it comes out, it does the singular apostrophes here. Again, I prefer the double only because I do a lot of like NLP, natural language processing stuff. And a lot of times with raw text, they have apostrophes in it, and that can sometimes make your code a little more buggy. So what I like to do is just kind of get it right from here. And I'm just going to go in the order that they came out. So I'm just going to go ahead and say, caret and paste it. Now, again, you can obviously type this stuff in as well. But for me, it's just been, I've made too many, I guess you could say keyboarding errors where, I miss something and then I don't like it. So what did we want here? Oh, we did not want those two. So cut and color, I forgot there. Those were going to be our categorical variables. So let's go ahead and skip. So caret and then depth. That's what I want to jump to. So depth was our next one. And again, if you want to just type them, that works as well. This is just a nice way to kind of see all the names, especially if any of your names are longer. You can see them this way as well, as opposed to kind of looking at this. Like if you have a ton of columns, sometimes you'll get those periods in the middle where like you actually can't even see what's all the way to the right. Whereas when you call dot columns, it'll show you everything. So I'm gonna go ahead and pause for about a minute at this time to make sure everyone has a chance to get caught up. And I updated what I have so far as well into that shared file. Why I'm skipping over our cut color and then awesome. So yeah, if we go back up, so back up to here. So I had cut, color, and clarity. Those were category types of variables. So if we think about what that represents in terms of data for cut, color, and clarity, if I look back up here where I've seen this, cut, color, and clarity, these are going to be non-numerical values. So cut, the different like words they use. Color was this scaling here of just letters. And then clarity was giving us these different like labels as well. So because we're using a quantitative visual here, so we're going to be using histograms, that's why we had to skip over those. So if I included those, it's going to give me an error there. Why we're skipping over these three. We're going to use those in a different type of visualization next. And then before we run this, the last thing I'm going to do here is just put in a little bit of titling. So a lot of times when you use this subplot method, a lot of people get stuck on where it's PLT dot title. And then what happens is it just looks weird. It's kind of like leftward and like it's right on top of some of the graphs and you may be covering something. So whenever you're going to do a combined plot like this with subplots, I suggest using the argument of subtitle, so super title. And then what that input's going to look like is your name. So I'm just going to say distributions of quantitative variables. And then what we want to do here is a positional argument here. So I like to use y is equal to 1.01. And what that's going to do is give me a little bit of a gap between like all of my graphs and where my title's at. So it's just like embedding some white space in there to make it a bit more reasonable, or readable, I should say. And then lastly, you can just pick your text size. So when I usually do it with this kind of setup I have here, so going off the fig size I have, I keep it a reasonably close number. You can play around with how big you want it to be depending on the audience you're working with. So I find 16 just as a font size pretty useful there. Then if we go ahead and say plt.tight underscore layout, what this does is just kind of get rid of like that buffer space in between our plots. It just makes it a little more viewable on screen. And then lastly, just so we don't see like all the object and printout stuff, plt.show gives us just a nice clean visual printout. So once we have all this, we can run it. I forgot a T. Awesome. See, now you guys understand why I always try to take really good notes for myself, because apparently I just spelled palette wrong here and correct here. Okay, awesome. So now we can actually see it. So I'm gonna go ahead and fix that in the copy and paste code I gave you guys as well. All right, so this is the code we executed. And then down here is what we have. So cool thing here, it goes in that same order we put it in. So again, we can kind of see these names here being listed. So it's our carets, and then it gives us our frequency distribution here. So these are histograms of count. So the variable on the y-axis for each of these is going to be count. You'll see we have this last one here, it's blank, which we kind of planned because we said we only had 7 quantitative variables. So we knew that that last one there would be blank. Now, pros and cons to this type of thing is that when we put it all together like this, it's sometimes hard to do a side-by-side comparison. But what's nice is that we get our unique axis plots here. So the counts are unique as well as the x-axis. I don't like doing shared settings and stuff. Some stuff you might be able to see like where you share an axis between certain ones. Because all these variables are inherently different, I like to kind of see them just how the program is going to suggest that they should look in terms of their dimensions here. So we can kind of see some of the different distribution shapes here. Like for example, I can see price is heavily skewed. So since pretty much all of my data is on the left here, I'd say this is a skewed right distribution. So I know that when I'm working with this data, some of these higher prices here may not be ideal to work with. Only because like here, so if we're at 15,000, 5,000, I could see the majority of my data is going to be below that 5,000 mark. So when we're looking at price, this is something that if we develop our model at the end and we're not happy with it, we may want to go back and kind of redefine our goals. So maybe we could go back and try removing some data. Like for example, maybe I'm, for my shop, I'm going to say, okay, I want only data less than 10,000. Like I want to look just at that data and see how accurately I can predict in there, as opposed to including those higher values. So that's something, again, I never suggest pulling data before we have to, but it's one of those things, like it's a choice at the end you can make. Everything else here, we're looking at depth is pretty normally distributed. Table, kind of a weird looking one, but we can kind of see like in generally shaped, like it's all got a pretty small interval there with a nice peak in the middle. Caret has a little bit of skew to it. Like we can kind of see this higher frequency up here. However, it's not quite as noticeable as this. We don't see as much like extreme dive there. And then our X, same thing. While we do have that, kind of bimodal behavior here, it's pretty similar to Y and Z. So we can kind of see all those distributions are fairly similar, which makes sense there for X, Y, and Z because those are giving us dimensions. So they should all be fairly similar looking distributions because diamonds are cut to like a certain shape typically. So that's a good way of getting that data to visualize where it's at. We could also do this with going to be box plots. So if you want to look for like anomalous outlier behavior. So what I'm going to do is I'm going to do a copy and paste here just to save myself some time. So if I click in here, do Control A, Control C, Control V. Oh, sorry, don't Control V, that's just pasting it. So Control A, Control C. What that's going to let me do is go ahead and paste this code down here because all that's really going to change is a little bit of this to get some nice box plots to look at this data as well here. So in our first argument here, what we need to do if we want to get box plots is we need to specify either a Y or an X argument. So, and that's kind of an update too, you might not see in others, and a common error code there is we want to go ahead and say, I like to use Y equals for all of these arguments here, because what that's going to give me is like the vertical box plot. So typical, if you're an Excel user, you can kind of see it that way. Everything else is the same except for this part right here. Instead of a hist plot, we're going to change the word hist to box. That's one cool thing about using these in combination with one another is that you can, make your life pretty easy with the copy and paste feature there in a couple revisions. And we could also combine these as well if you wanted to go ahead and say, like, hey, like, maybe I want to have a histogram here and then a box plot here, or like, histogram box plot and have the same variables that way. That's another cool way of doing it as well. And then what I'm going to change here is my title. I'm going to say outlier analysis of. All right, so when you run that, we get this. So we can see some nice box plots here. Now, this is why I like kind of combining the two looks here. So when we get a histogram, we can kind of see general distribution shape. So if you're looking at understanding all of the different possible distributions, last week I recommended a course here that we built with Eduonix, where I handled all the videos. It goes through everything. It also, there's an e-degree option as well. But that course was the statistics in data science. So it was really focusing on kind of a better, deeper understanding that we don't necessarily have time for today to cover. Of how to really work with this. So we're going to kind of do a crash course in that today. And these are my first two tips for everybody is when you get a data set, like plot it, look at it visually, and then using the box plots here. Now, what a box plot gives you is not only the shape of distributions, but it also shoots you with outliers. So the general steps for looking at a box plot, if you think back to way back when you did these as a kid, is this is the order that they're calculated in. So the first thing we do is we find the median. And I'm typing this in the chat as well, so you all know. So we look at the median, and then we go ahead and we're looking at our upper and lower quartiles. So we're looking at Q1 and Q3. We remove outliers from upper lower fence. So that's typically 1.5 times whatever the IQR is, or the interquartile range. And then we recalculate max and min. So those are kind of the like by hand steps to doing this. Now, obviously there's nothing you're ever gonna want to do by hand in data science, but that's kind of where these come from. So our maximum value is up here. So these are modified box plots to account for that. So what we'd truly be treating as a max value, if we wanted it to be a normal distribution or a normal-ish distribution, would be in between these two bars here. Same thing here. So those upper and lower bars there kind of give us like, if we want this to look really, really useful in a normal distribution, that's what we want to strip. Now, as I spoke about earlier, when it comes to what we can remove, this is where you would enlist more of a, what we call an SME, or a subject matter expert, because when you're working with obscure data like this, like I don't know a whole lot about diamonds. Like I don't have another side business where I, grade and sell diamonds. So I would not feel totally comfortable saying like, okay, like we should remove stuff without a doubt because like those don't occur. Maybe it is a pretty common thing to have whatever this value up here is, right? So a Z, a measure that's like way off the charts compared to the rest, right? It's possible. I don't know enough to, really say one way or the other. Same thing here, like these inherently look gigantic to me because they're like way off the charts of the data. Same thing here, like this 0 value, or maybe that top one, I don't know. Here, if I'm visually looking like, yeah, like this, for table, like this one way up here really kind of looks odd to me. However, when I look at depth, those outliers are actually pretty symmetric, right? So like I have just as many as on the top and on the bottom. So maybe this one is just a really unique distribution. However, when I'm looking over here, again, a way we can do this. So at this point, I'm kind of going to just guide you in the executive decision of some data we're going to remove. The main reason being I want you to have an example code of how to do that. So if I want to look here, let's look at price, because that's what we're trying to predict, right? Our goal by the end of today is to predict price. And I could see there's a steady stream of outliers that are just way above that max value. So if I'm looking here, that max value is pretty close to like 12,500. I'm going to scroll way back up to the top here. So that max here for price, it was actually going to give us a little over 18,000. And then it said everything above that was kind of where it was deeming them as outliers. So if we looked, same thing here, we kind of seen these up here. So the difference between these output tables is this gives us a true maximum. So when you use .describe, it gives you the actual maximum. So this is the actual max. Whereas if I look down here at our visual, we could see that like that's the actual max. This is the calculated or the modified maximum of where we can kind of get rid of those outliers from. So a way we're going to go ahead and clean this data up a bit is I'm going to try to redefine my model and say, you know what, I don't want to predict price for any diamond. I want to predict diamonds at, under a certain price point, because I'm guessing that these same values are where I'm getting these extreme values from. So I'm going to get rid of some of my higher priced ones, only because I could say like, okay, like this one is probably that highest price one, right? If it's a crazy high value here, that's probably where we got that 18,000 from. Maybe that's where my big table comes from, my big Y. So we're going to do a little bit of data cleaning here to remove it. Now, like I said, in your real practice life, when you're going to remove data, you want to make sure you have a justification. Like, sometimes one crazy data point can have a big effect on your model depending on how much data you have. So as long as you're kind of documenting that of like why you're doing it. So for example, here, let's go ahead and give ourselves a little practice justification. So maybe I'm just going to throw a statement in here, and I'm going to say spoke with SME. So that stands for subject matter expert. And we're going to go ahead and say that confirmed, we can remove diamonds with a price above, maybe we're going to go ahead and just cut this off at like 10,000. So I'm going to go ahead and say above 10,000. So anytime you're going to do some type of outlier remove, and there's ways to do it too, like where if you're working with data sets, again, you can use that stats background, like, okay, like, hey, this is more than, 2.5, 3 standard deviations above, like probably not something I want to work with. But again, a lot of times in industry specific fields, it's less on the stats and it's more on the business intelligence side. So I've done reports where like, this is a line that they draw. They'll say, hey, look, like, anything above this, like it's not a huge thing we're really worried about. We're looking for a model that just focuses on these kind of more common items we're working with. So that's an example note there. We can get rid of anything above that price tag. Now, to do that, we're gonna go ahead and make a new data frame. So let's go ahead and make our new data frame. This one I'm just gonna call df_diamonds. So kind of sound like it's our clean version of the data frame. So what we're gonna do here is we're gonna take everything except rows where it's greater than a certain price. So to do that, we're gonna go ahead and say it's equal to df bracket df, and we're gonna go ahead and reference that price column. And then I just wanna use the argument here of it's less than 10, 2, 3, 4, 10,000. I'm just checking I put the right amount of zeros there. So this is a way of just going ahead and getting that data, and I'm gonna go ahead and throw this in the shared as well. So what that's doing is it's gonna take my big data frame and it's gonna say, hey, I only want the rows where the price variable is less than 10,000. And to check that, so if I look at my original DF, here's the shape of that. And if I say my new data frame diamonds and I get the shape, we can see that there's notably less rows there. So if I want to see how much I got rid of, sometimes I forget Python's a calculator, and you could just do stuff like this. So we can see how many rows we removed. So maybe give yourself that note. Like I've done tutorials where I write like a really complicated statement to determine the difference in the number of rows between two data frames. And I sometimes forget like the easiest way to do things is like Python is a calculator. So you can just do a shape argument and then just subtract those number of rows. So rows by columns, that's kind of how the shape argument works there. So we removed about 5,000 rows of data. So maybe like, like 10% of the data or so. If I looked at like that, see what percentage of data was removed. To figure that out, I could just take that amount and then go ahead and divide it by my total. So we removed a little under 10%. But again, in this case, while we removed that data, it might also give us a really cool model. So that's one thing I would suggest too, is when you're working on a project, don't be afraid to take it a little bit in your own direction. Like if your boss or supervisor, client, whoever it is, tells you like, hey, we want this, I want a model on all my diamonds. Cool, I'm gonna make them a model on all the diamonds. But I'm also gonna use my executive reasoning as a data scientist to say, hey, like that model might not be the best because you've got some extreme values in it. So not only did I do that model for you, I also did this more refined model. I, scooped off the top 10% of data, and now look at our accuracy. Look at how close these, how high our R squared is now. We're making really good predictions. So this is kind of an example of where you would maybe say, you know what, like this model kind of looks weird with this much, extreme values. Let's see how good I can get if I cut off that top 10%. All right, and then what I'm going to do is I'm just going to go ahead and copy and paste my box plots here. So I'm going to go ahead and say Control AC, and then do a Control V. And then what I'm going to change here is the data frame that I'm referencing here. So now we're using that DF diamonds. So what we're going to do is I'm just going to go ahead and change up that naming a bit, just to get a new data frame. You guys will notice that I'm, again, one of those people, like I'm a big fan of copying and pasting. So that's why I stick to certain naming conventions. So, if I'm naming it DF underscore something, I always keep it that way. That way I know like I can copy and paste that variable later. Maybe we'll rename this cleaned. So we removed some. So I'm gonna go ahead and pause for about 2 minutes here while you guys get caught. Well, not 2, shouldn't take that long. But so what I did was just copy and paste the box plot. And then we're just renaming this with the diamonds, so underscore diamonds after DF. So I'll give about a minute or so to get caught up on that. And I'm gonna go ahead and paste this in our little repository code there as well. So when we run that, you can see we definitely stripped a good amount here. So we got rid of some. We still have this really weird value here in our Z. So maybe you want to go back and specify like, hey, whatever this goofy Z value is here, like I want to remove that one, or maybe this high Y, but our price variable does look a lot better now, right? So we don't have as many outliers on top. We can kind of see some adjustments here as well. So it's looking a little better. One thing I do want to recommend is don't get rid of so much data. So what I would suggest here is there's a couple of things that are common words you're going to see as you learn more about regression, classification, predictive analytics, machine learning, is the idea of overfitting. So overfitting means you get your model so good on the training data that it actually hurts it when it uses new data. So going and taking that note here, so overfitting, a model is so specific to its training data, it actually gets worse with new data. So the idea of overfitting means I'm going to pump in so much clean data into this that the model never really develops for anything else. So we always kind of want to leave some in there. So like now I only have this one weird kind of like giant diamond apparently, which was like a huge Y and Z value. And like I'm going to leave that in there because like it's not going to kill the model. I did remove my price. So I'm like, okay, like I am specifying my data a bit here. I'm only looking at stuff, under 10,000. However, I'm going to go ahead and leave this crazy outlier in there. Now, again, you could probably remove that because it looks like it's like literally one data point. However, again, it's kind of up to us here, but we don't want to overfit too much. So let's go ahead and just leave it as it is for right now. And then let's go ahead and get rid of, actually, there's one more. What was the other thing I want to do? The weird zeros. That's what I want to talk about here. So I'm looking here at a X, Y, and Z that are all 0. So even though we had this high one in there, I don't know why a diamond would have like zeros in it. So let's just kind of explore that one a bit. So that was the one other piece I want to look at here because we're talking about dimensions and we have zeros. So what we're going to use here is a little kind of nifty command to identify just where our zeros are. So I'm just going to call this my zeros data frame. And to do this, we're going to say df diamonds. And then I'm going to use kind of a more complicated command here. So I'm going to type it and then talk you through it. All right, so what this is doing here is I'm naming a data frame of zeros. And let's go ahead and take some notes on this. So what this is going to do is it's going to pull my rows. So it's going to give me rows. So it's going to give me the rows where my X, Y, or Z values are equal to 0. So maybe we went and verified with that SME that like, hey, should an X, Y, or Z ever be like literally 0? And they're like, well, no, if those are in there, that's an error. That's an error in measurement. So in this case, maybe we've seen that. So we went back and talked and said, hey, look, like I'm seeing zeros here. Like, does that make sense? Should I have a 0? And then if we hear back like, no, like that's not a real value that we get, maybe we want to remove that bit of data because maybe the person who was, logging the data, entering it, tracking it, maybe they made some mistakes here, right? So maybe they hit 0 on the keyboard instead of a 1, whatever it may be. So we're going to go ahead and identify that. So the logic of this statement, similar to how we use that greater than or less than kind of splice above, here we're saying zeros are equal to the df. So these are kind of common here. The names are all the same. This command here is saying in this data frame, column X equal. So we have to use 2 equal sign there. And that's kind of a piece of how like Python defines variables. Like if I want to say X is equal to 5, I literally just type X is equal to 5 or X is equal to some string. So when we want to reference a specific, I think of the word like congruent or exactly equal to, it's my way of remembering that. So we use 2, and we could set it to a value there. This is also a way you can look for like string data. So I could say maybe equal to, whatever it is, like that ideal premium. I could find just those values as well. This is the OR operator, so it's going to give me everything. So and is this. This means if I had that, I would be saying I want x is equal to 0 and y is equal to 0. But in this case, I'm just worried about getting all the weird values. So I'm going to go ahead and use the OR. So it's saying x is equal to 0 and or y is equal to 0 and or z is equal to 0. So if any one of those conditions is met, it's going to give me that row. So let's see how many we got. 12. So we're saying that there's 12 different ones with some of these weird things here. So maybe I want to go ahead and just look at them all. And I can see that there's 12 of these data points now that are like just giving me some goofy kind of input there. Like they don't quite make sense. You know, why are all these z values 0? Like this one here, 1182 for our index. It's saying here that I have like no, so I'm guessing, you know, length with height, like it just seems like these are errors. And this one, like it's a very good diamond, but it has no dimensions. Like, and again, now maybe that's the case, but in a general rule of thumb here, I'm thinking that this was an error. And that's just kind of my interpretation of it. So again, when you're reading through your data, you do want to go ahead and reference like an SME and see if this makes sense. Is this a possible value? If not, I'm going to remove these. So we're going to go ahead and get rid of those. So a good way of doing that is another kind of cool command here to remove data based on what's not in another data frame. So I'm going to go ahead and type this out and then we'll talk through it. Okay, so looking at this command here, what this is doing is I'm just going to redefine that DF diamonds data frame. If you want here, you can maybe throw in a different naming convention, like throw a number at the end, capital letter. Again, it's kind of whatever you prefer. But for the sake of just simplicity in our naming here, I'm just going to adjust that original data frame up here. So I'm going to say DF diamonds is equal to itself, you know, such that this little tilde thing here, what that does is it makes it the opposite. So I'm saying it's equal to whatever is in itself, just not zeros. So it's the whole data frame except whatever rows match up here with zeros. And then the ones that don't match up, this kind of, you know, dot drop NA, and then the how equals all is just like a catch-all. So if I had any like weird stuff, it would, you know, just kind of remove that as well. So I'm gonna go ahead and run that. And then if we think way back up here, our original DF diamonds was, what do we have, 4877 or 717. So if I check the new shape, it should be less. Yep. So we took out those 12 rows there. So we've seen these 12 rows of data are now removed. So 48,717, subtract 12, we're here, we're good. So in general, we think over here, we want to think about context of when and why we're removing outliers. And then again, noting that we remove them along the way. Okay, so since we did a bunch of outlier removers, let's go ahead now and check out what these categorical variables are. So what I'm going to do here is just suggest if you want to look at something in terms of getting those categorical variables, you could use what's called a count plot. So there's some different ways of doing that. Oh, great question here. Why do we need that kind of tilde sign right here? So it's a little squiggly. So what that means is it's the opposite. So this is a great way if you want to keep everything except something. So maybe some notes there. So we keep everything except so it means like the opposite there. So here, instead of saying like, you know, remove specific rows, this is a kind of a shorthand way of removing everything that's in here. So it's saying I want everything in DF diamonds except what happens to be in here. So when we're looking at categorical values here, some options that we have is going to be looking at count plots. However, for the sake of time here, we are getting close, so I don't want us to go through it. So what I'm going to suggest is, if you want to do visualizations with categorical variables, look at, I'm going to paste this in the shared code as well, actually, so you guys can go and check that out if you want. So I did paste it in there. There's an example of how to do some cool categorical stuff. But for the sake of time, we're going to kind of skip over that a bit. We're going to talk more about how to work with that data. So if again, you're looking at shared code, it is there. However, we're going to kind of skip over that a bit today, just for the sake of time here. With that categorical variables, so what we can do is, let's go ahead and, basically what you're going to get is this. So if I go ahead and just throw this in here real quick, and this is in the shared code. I just want you guys to see it. So the count plots just give us these nice little arguments here. This is something that is kind of annoying if you don't have it handy. So a lot of the label rotation stuff, when you have a multi-plot, getting these labels on the bottom to rotate is like a really annoying thing, actually. So having this bit of code handy is really useful. And again, you can copy and paste that. I just threw it in the shared file there on the Google Colab, just so you guys could get that one quickly and we could talk through it. So in a count plot, what it's looking for is, think of bar graphs. Just instead of calling it a bar graph, I like using the count plot from Seaborn just because it gives some more versatility with it. Here we can kind of see the different frequency of things. So for example, I could say from this data set, I'm really not having very many fair or good diamonds. So most of my diamonds are of these, ideal, premium, very good quality. In terms of the color distribution here, this one you might want to be kind of cautious about, because if we remember back at the top, it said that there was actually a preferable kind of ordinal order there. So that's something, if I was going to really use, I would probably want to go get some more data on. And then same thing here with clarity. I don't know enough about it. Oddly enough, it looks kind of normally distributed. But again, you want to make sure that these are ordinal values, you have good notes on those. But now at least you've got some nice sample code here of how to use a count plot. So for the categorical side to it, you'll see most of this is the same, as well as this piece down here. This, like I said, if we want to talk through, this is a for loop. So it's saying for the axis in my figure.axis. So this is the figure itself, and then the axes are these kind of bottom ones here. So this is saying to rotate those labels 90 degrees. So it's kind of rotating everything at 90 degrees. And I did that just as a way of fixing the bottom here. It didn't really make much of a difference here on my vertical axis, but like on the bottom ones, it's really ugly if these things overlap. So that's a way of getting that here. And then this, you can kind of see here, same concept. You could change these to Y's if you want to. That'll kind of make your bar graphs go sideways if you want. So if you change these X's to Y's, however, I'm a vertical kind of person, so I like them this way. But again, pretty similar stuff to the last one. We changed up the fig size a bit just because I only had 3 instead of 8 or 7, I should say, from like our quantitative. So this kind of gives you an idea too, just looking at your data, what conclusions you can make. So if the goal was here saying, hey, look, I just want to learn about fair diamonds data, I would say, okay, well, we don't have very much of that, so we're probably not going to learn much from it. However, if I wanted to work with just maybe ideal cut diamonds, maybe I could specify that to there and see what that data looked like. So looking at categorical visualizations gives you an idea of like what can you even try to model based on the data that you have. All right, now let's go ahead now and start talking about how to include some of this stuff in our model. So maybe we want to include like one of these variables in here. I will say whenever you want to include a categorical style variable in, the key thing to consider is going to be exactly what it is. So we want to think, okay, like what can I do with this? What can I, how beneficial is something going to be for me to include in there versus, maybe not including it. So this is if we want to include a categorical variable. So a lot of times those are really useful. Typically if it's like a binary output. So if we have like a binary output of like, if I'm thinking about used car sales, right? So I could say, okay, the car did or did not sell within 2 months. So if you could binarize variables, that's a great way of saying like this occurred or it did not occur. So zeros and ones, those are pretty useful when you're looking at like the idea of like success versus failure. Models typically work really well on a binary basis. However, we can't always do that. So maybe here I could say like, okay, it's either, you know, at least very good or not very good. But I want to give you a more kind of broad scoping of code. So let's say I said, okay, I don't want color, I don't want clarity. Like there's just too many options there for this to be useful to me. However, I'm really concerned about cut. So maybe they're saying, okay, like, hey, look, we're very focused on the cut of the diamond. We want that included in our model. So whenever we want to include a categorical variable into a model, a good way of doing that is what's called one-hot encoding. And then we're say using dummy, spelled dummy wrong, dummy variables. So what this allows us to do is to take something that's like a textual categorical category indicator and encode it in a way that allows us to use it into these regression-based models. So to do that, I'm gonna go ahead and type out the command and then we'll talk through it. So I'm just gonna call this, I'm gonna give it a new name. So I'm gonna say dfx. You can name it whatever you want. Again, the naming convention is kind of irrelevant. This is just how I typically name things. So dfx, and I'm gonna go say pd.get underscore dummies. Our data is equal to, we still had df diamonds up here, right? Where are we at? Yep, that was our last one, good. So again, making sure you're referencing the correct data frames here. All right, so what this is gonna do is I'm gonna create a new data frame, dfx, and I'm gonna say it's equal to pd, so I'm referencing the pandas module, and I'm using the package here of get dummies. So what that does is it's gonna take a categorical variable and it's gonna take each of the possible outcomes. So we're gonna see like 5 new column rows, and then it's gonna say, okay, is it option 1? Is it ideal? If so, it's gonna assign a 1 to the value of ideal and everything else gets a 0. Or if it's a very good diamond, then the output's gonna be 0, 0, 1, 0, 0. So this is saying where our data is coming from, and then it's telling me the columns that I actually want to get dummies for. So we're looking at just cut. So I'm gonna go ahead and run that real quick, and then let's take a look at what that looks like. So I'm just gonna say dot head, maybe let's look at the first 3. So if we're looking at this, we still have all of these original columns in here. So we have caret, color, clarity, depth, everything going through. And what it did here is it took that original variable of cut, so cut was up here, right? And it just told us which one it was. So that first column here after caret was cut. So if I look at these kind of side by side, right, here's our original table, and here's after we use that one-hot encoding or that getting dummies feature. So in this case here, what we got was we started with, this was our original table, and we said, okay, I want to include cut, but like I don't know how to use words as numbers, and that's again a very common thing we occur with. So by using the get dummies feature, I got rid of this column. So notice cut's not here anymore, and it gave me these 5 new columns. So it put them in there, and then so in this first case, the way I read this is the first one, this diamond is an ideal cut because it has a 1 that stands for true, and then the remaining columns are zeros. My second one here is a premium cut because it has a 1 and then all other are zeros. The third one here in the index of 2 is a good cut because all the other values are zeros. Now, we could technically include this for everything, right? I could have done this same thing. So I could have changed this command up here and I could say cut, comma, color, comma, clarity, and I could get all kinds of 1s and 0s in there. However, you need to think bang for your buck, right? The more data you introduce, the more things your model has to consider. So the best models, I mean, if you could make a model that predicted at 85% just looking at one thing, that's amazing. That the simpler, the better thing of Occam's razors rule here. The simplest answer is often the best, and the simplest model is always going to be the best because that way it doesn't have as much to worry about. So here, maybe we're just going to go ahead and include that 1 extra dummy variable there. Now, what we want to do here before we go ahead and get into finalizing and building this model is we want to go ahead and see what it is we're actually going to use. So for example, I want to get rid of these two columns, right? I want to get rid of color and clarity. So I want to go ahead and get rid of those. Now, to do that, what we can say here is just one kind of way of copying and pasting. We've seen dropping options earlier. What I'm going to do here is just kind of give you another less fancy way, I guess, where it's a little more like kind of user defined of how to copy over a data frame. So the first thing I'm going to say is like, let's go ahead and get our columns handy here, because then we can copy and paste. And you'll notice that I'm a big fan of copying and pasting because it avoids typing errors, such as spelling palette wrong like I did earlier. So I'm going to go ahead and make a new DF here. So I'm going to call this DF final, because this is our last bit here before we do our application piece, our modeling. So what I'm going to do is I'm just going to copy over the data I want from this one. So I'm going to say DFX, and then 2 brackets in here. And then on the back end of that, we're going to go ahead and just say dot copy. Now, what we want is just the things we want from in here. However, the way I suggest that's the easiest way to do it, is just to literally highlight all of these. So all those different columns, do a copy, and then I'm going to paste that right in here. So for what I want to get rid of, I would also suggest backspacing this just because it looks a little neater. So you'll notice like if I do a enter here, the lineup is a little different. So that's something to be wary of when you copy and paste sometimes. So like when I copied this, it looked kind of weird, right? It was like over here. So I just backspace it to one line. And then if I don't like how it looks, I hit enter again after, just to have that nice kind of vertical alignment there. So if we think about what we don't want here, I don't want color, right? Because we never set that up with the one hot encoding. So I'm going to get rid of it. And then I don't want clarity. So now what we have here, we have our caret, depth table price, X, Y, and Z. The zeros part. Okay. All right. Give me 1 second while I go back and snag that zeros. So I'm putting those zeros ones in there now. All right, so if you're looking for that zeros fix there, it'll load into Collab in a second. So what we did here was we are just picking out the columns now that we wanted. So I'm going to go ahead and say this is our final data frame, and we're just going to pull these. So we have our ones at the end here. So we have those 5 that we did the dummy variables on, as well as everything except color and clarity. Go ahead and run that, and I'll put that over in our share file as well. All right, so we've done a ton of cleaning here. We've done a ton of visualization. Now it's time to get into the actual modeling piece here. So the first thing we're going to do is we're going to use that train test split feature we talked about earlier. So I'm going to type it out, and then I explain our way through it. All right, so what this is doing here is this is, like I mentioned before, kind of an industry standard way. If I go way back to my imports here, this one of splitting your data for training and for testing. So that's our first line of the code there. And then what this is going to do is it's going to create 2 data frames for me. So it's going to give me a test data frame of 0.2, so 20% of my data. That's kind of the typical there. You reserve, you hold out 20% of your data for testing at the end, and you can use 80% of it for training. You can play with those. Sometimes you can get like 30% in your holdout, whatever it may be. However, kind of 20 is like that standard. I always set a random state equal to something. as we've talked about in previous lectures, what that does is it just makes sure that every time I run this code, it pulls the exact same data into my testing and my training, because some of those times it's like if you don't set a random state, you might just get really lucky and it pulls like the greatest training data ever. But again, with the random state set there, you make sure you have that version control and consistency. Next things we're going to define here is I'm going to define my training data. So I'm going to say x underscore train is equal to my train df. And then I want to go ahead and, since I'm using my training data here, what I'm going to go ahead and do is drop that column of price. So we're going to say dot drop columns price. And then my axis is equal to 1. So this is creating my X, or my input training data. So the reason why we're removing price is because if we tell it what the price is, it's going to be like ridiculously accurate, right? That's like saying, what's the weather right now? Like you could go predict it right now because you can walk outside and find out, but that wouldn't really help you predict it in the future. So that's going to be for our training. I'm going to go ahead and just do a copy and paste here to then get my X testing data. So for my testing data, I'm going to be looking at my test data frame. And we're also dropping that price column because, again, we don't want to tell it the answer. Then here for my Y training data. So I'm again going to be using that train data frame. And then I'm going to be doing a little bit different here. So this case, we only want the price column. So I'm just going to go ahead and say price. And then for my Y test, we just say there price as well. So what this is doing is just creating our training. So for my X train, it's going to use this data to predict Y train. And it's going to refine itself based on how accurate it can predict those things. And then for my testing data, this is the stuff I'm holding out that I'm going to actually evaluate that model on at the end. Let me go ahead and share that over. All right. Now, what we're going to build here, this one's going to be a lot of, I'm going to code it and then I'm going to share it kind of thing. For the sake of time here, I want us to focus more on the evaluation piece. So in this case, what I'm going to do is I'm actually just going to go ahead and share this over in the collab file. Just because this is one of those, we talked through it before using something similar like this. So I'm going to go ahead and just share this, and then so if you check out that collab file, you can now copy and paste this gigantic thing here, which is going to be this. And we're going to talk through what that means in a second. So please check the collab file now to get this giant code block, just because it's a bit easier for us to talk through this than as opposed to having to go ahead and code this from scratch. Now, just because, again, I'm encouraging the copy paste method here, it's not that I'm suggesting it's not really useful to understand every piece of this, but again, like, I don't want you to, become frustrated after 30 minutes of typing out this code. Like the first time I created this, like this took a long time for me to, error check, get it right, explain every piece in it. So I tried to do my best here to comment it out so you can understand each piece of what's going on, because that's, again, the goal at the end is that you not only can use it, but you can understand it as well. So I'm gonna go ahead and talk through. So we did need one new import that truthfully I forgot to put in the top part there. So that's our cross-validation score. So that's the CV thing you'll see referenced throughout here. For those of you that were with me last week, we built something similar to this when we used a box plot to evaluate our modeling as well. So this is something you'll see I kind of keep handy, a couple different variations of it. So this one will look a little different. You might like the way this one looks better. You might prefer the way the other one looks. This is personally one of my favorite ones because it looks a little cooler. So what it's doing here is I'm naming my features and targets. So I use a copy method here to go ahead and get up there. So features are what the data we want it to learn from, and the target is what it's aiming for. And we're using our training data there. Here I defined the models. So we looked at a linear, elastic net, random forest. I also include a random forest regressor in here, ridge and lasso CV, so cross validation. So these are like specific kind of ways of looking with linear. So these three kind of go in tandem. If you want to learn more about those, you can Google them and they will show up. Those are the ones we imported way back up here underneath from scikit-learn. So scroll on back down, going into our next part here. What we did was say the number of cross validations. So 5 is like a standard number. You can change it if you want, but as I kind of talked about last week, like it's not going to change your results a whole lot. It just takes longer to run. You don't want to necessarily go less than 5 because that kind of will defeat the purpose. So cross validation is just how many times it's going to execute this thing to see your results. Here is creating a data frame. So it creates a data frame based on the range and the length of models. So it's saying how many are in here. So if I had 10 of models, it would then give it a length of 10. So it's going to be a little output thing we're going to use at the end. My entries in it, it's a blank list. So we use the brackets here. You could also use something like this if you want to. I just like using the brackets. It's the more, again, Pythonic way of doing it. And then here for this part, so this is our outer loop and our inner loop here. So this is for model in models. So for each of those model options, this is accessing the model name in the class. So this is actually pulling to the documentation saying, what is the name of this thing? So that's how we can get the nice statements in the printouts. The accuracy is here. So for our accuracy, that's a general name. I'm not gonna lie, I use this also a very similar set of code here when we're gonna do classification, which we'll look at tomorrow. So you'll kind of see the same thing there. So here it's saying, okay, we're looking at the model. So this is that cross-val score import we used. Look at the model, here's the features, here's the targets, what I'm using for scoring. So like we talked about earlier when you use R2. And then for CV, my cross validations, it's saying a number. So I could delete this line of code here and just put a 5 here. But again, I kind of like to specify it up top. I find it a little more understandable that way. And then what this is doing is it's going to enumerate. So it's going to list out, go through each item of my accuracies, and then it's going to add them in with this dot append here. So typically a cross validation in, kind of statsy terms is references a fold. So a fold meaning each time you're, iterating through and getting that, and it's just appending it with that value there. Lastly, we're going to update that data frame here. So my final data frame output that I'm looking at is the entries, which we appended. And then our columns, I want the name of my model, our fold, and then that R2 score. So it's going to say here, what are each of these items? So fold means which time it went through, and then the accuracy that came with it. And then what else we want to do is just go ahead and visualize these results. So I'm going to go ahead and just use the box plot here to kind of see what it looks like before I do any more analysis. And this is kind of similar to how we talked about last week. So I just made this one look a bit cooler, at least in my opinion, cooler. So when I run that, you're going to notice this one's going to take a second because Diamonds is also a pretty large data frame. So hang tight while that runs. If you want to make this run a little faster and not get the nervousness of watching this, you can split these two. You can split the visualizing part into a different cell block. I just, for the sake of time, figured that'd make your copy and paste a bit easier. So hang tight while this executes. I can hear the fan on my computer kicking in. All right, let's check it out. Okay, and we now have a terrible visualization. Now, I promise you it's going to look way cooler in a second. From looking at this, we see we have our R squared value, right? So we know that R squared closer to 1 is good. We talked about that before. Awesome. Okay, so looking at this here, what happened with this is we have 3 that look pretty similar, 1 that looks the best, and then 1 that's so low, it's actually kind of confusing everything else. So what I'm going to suggest is let's go ahead and just get rid of that elastic net CV. So you can either copy and paste this whole thing and run it again. I'm just going to go ahead and do that. So I'm going to say Control A, Control C, and then I'm just going to run it again. The only thing I'm going to do is get rid of that part where it has the elastic net in there. So this time when I run it, that elastic net won't be in there because that was such like a weirdly low visual. It kind of made the rest of the box blocks not ideal there. So as we're waiting on mine to run here. All right, got it. Okay, so hopefully that gives us a little bit better of a visual here. So things I want to talk about, because this box plot is a little bit of a more fancy looking version than the one we used last week. So these dots here are going to give us actually our cross validation. So you'll notice each box plot has 5 of those dots. So what it's saying is those are the data points used to develop the model. So the CV is equal to 5. That's why we have 5 dots. If I set CV equal to 10, please don't, it'll take really long to run, then I would have 10 dots here. And then we could see here we have our box plots. So we see here, these are the actual values it got for R squared. And the box plots represent the distribution of those values. So we can kind of see a clear winner here. That random forest regressor is going to kind of really stand out as our best bet here. So that's kind of showing like, hey, this is the best. If we want to see how much better it is, we can kind of look at a nice little way of printing out a group by statement here. So what I'm going to do here is I'm going to go ahead and say, let's get our average of R squared. So to do that, I'm just going to call this my compare. So the comparison, what I am going to reference is this CVDF. So this thing up here, CVDF, it's a data frame. So let's go ahead and take a look at what that looks like first. So that CVDF, it says the model name, the fold. So it had 1, 2, 3, 4, 5 iterations. And these are the R squareds that it got. So a nice way of looking at this is going to be just take the averages here. So I'm going to go ahead and get some averages with a group by. So I'm going to say comparison is equal to CVDF, and I'm going to say dot group by. And then I'm going to go ahead and use model name. I want the R2 score, so model name dot R2, and I'm going to take the mean. And then let's go ahead. I'm going to say I want to reset the index. And then I also want to sort it just to put my highest value on top. So I'm going to say that sort underscore values. What I'm sorting by, I'm going to sort by that R2 value. And then I'm going to say ascending is equal to false. Then I just want to go ahead and show it. So I'm just going to go ahead and say comparison. Oh, what is it not like? Where is it not liking this? Oh, I have an extra underscore. There we go. R2 is not defined. What did I call it up here? Why is it not liking this? ADF group by. Let me try running it this way. Why does it not like it? I mean, R2 is not defined. It's right here. This is what I need to do. There we go. All right. So a couple of different ways there. You've seen I actually changed like the dot method for referencing a column. I typically use this one because it kind of gives you a naming convention. The way you've seen it before is I had a period dot R2. So that's another way of referencing a column. I'm gonna go ahead and throw this over in our shared code as well. So what this does here is I'm creating a new data frame just by taking the averages. So I'm grouping by the model name and then I'm averaging these. So for linear regression, we took the average of these first 5 here. And then resetting the index takes it from looking like a weird group by object into a nice data frame. And then sorting values just says, hey, I want to start with like the highest one on top. So what we see here is that our random forest regressor had the highest R squared. And we can also even look at the visual and see it's clearly up there. Even like the worst random forest regressor was better than the best of these. So we can kind of see that one was our optimal solution there. So for telling that's our best modeling feature for predicting these diamond prices. Now, where you're going to be ending class today, so going into looking at your homework assignment, is you're going to be going through what's called optimization of this model. So I'm going to copy over some code for you guys into that shared file so that you can use. And what I want you to do is we're going to talk through it a bit here. So I'm going to go ahead and share over that shared file again, and I'm just going to be putting some stuff into the bottom for you. But first, let's go ahead and talk through that assignment. So this is your end of session project here. So what you're gonna be working on is the execution of a grid search cross-validation process. So what this is gonna do is it's gonna optimize your random forest regressor. So in this case, we're gonna see, we've seen it work the best, but let's see how well it's actually gonna work. So we're gonna go ahead and see here now, all right, if we use this, what's the best possible way that I can do it? So the reason why this is going to be left up for you guys to complete is because these different options here, again, it's very dependent upon your RAM and your processor on how long these might take to run. There's been times on large data sets where I'll walk away for 30 minutes and this is still running in the background. And then there's times where, you know, sometimes if I run it, it's like, oh, like 4 minutes and we're done. Like, cool, great. So again, this is going to be code that I'm going to share over with you right now. So the goal is for you to figure out which is the best model. So to do that, I'm gonna go ahead and just pull over this collab notebook so you guys can get the sharing from there. And I'm gonna bring in some of that code. So this is the grid search cross validator. This here is gonna be your regressor. So it's saying what to use. The random state here, I'm gonna go ahead and set to 1, just so it's the same as before. But again, that random state number doesn't actually matter. You can pick whatever number you want, as long as you keep choosing the same number, basically. This is applying the grid search. So let me go ahead and copy this over and then we'll talk through it. All right, so here, what we're doing is go ahead and put some space in here. So this is like your homework section. So you're pulling in this model selection here from grid search CV. So grid search cross validation. And then what this does is it's going to optimize this model. So we said, hey, look, like this model was already really good. Oh, it's not the right one. There we go. It's already pretty darn good, right? That's a pretty high R squared value. It was notably outperforming the rest. And we even had less of an issue with like extreme values. Whereas for these two, especially linear and ridge CV, we had some pretty low values in there that were then kind of balanced out by the highs. But like I said, this random forest regressor did a really good job, right? It was all kind of together up here. So we're choosing that as our model. This, the number of estimators. So if I want to see more about a random forest regressor, so let me go ahead and get some notes for you guys on that, just so you can kind of get a little more learning in that case. That gets you to this page here, our random forest regressor. So it talks to you about the different options in there. So the number of estimators, the number of trees in the forest. So the default here is 100. So I'm going to try some different options there. The different criterion here. So mean squared error, mean absolute error. So the different options we can have in there, MSE or MAE. So we definitely, since there's only 2, we want to try both, see which one gives us a better result. So these are the different kind of command options we can have in here. So this is the most complex looking version of this model. However, again, we want to see which ones are going to give us some optimization. So for sake of time here, I just threw in a handful here for the estimators for you to run. So 50, 100, 200, 500, seeing those 4 different options. And then we're just going to look at the criterion of mean squared error and mean absolute error. So we're seeing which one helps us better understand the data. When it applies the grid, so it's saying, hey, use this package here, the grid search CV. I'm going to use my regressor. So you could type this right here, but again, when we can make naming conventions more clear, I try to stick to that. How I want to score it, I want to look at R squared. This time I threw in 10 cross validations just because I'm optimizing a model, so I want to give it as much as possible. If you're running this for a while and it's not working, you could switch that to like 5 there if you'd like. But for the sake of optimization, sometimes then I do crank it up to 10 and just give it the time. The refit is going to be true, ID identical and identically distributed. We're going to go ahead and default to false. And then our verbose, what this command does, which took me a long time to learn myself, is it tells me how much of the output I want to see. So when we go to verbose here, where are we at? Does it even say it in here? Oh, it's a random forest regressor. So what verbose does is it like how much like output you want while the program's running. So if you set this to something higher, I would say use 0 or 1. It kind of gives you like output of like what the program's doing, so you can kind of see how close it is to being done. Here, So I'm saying, giving you that reminder, this may be 10 or more minutes here to apply this. So when we fit the data on features and targets, so you have all those features and targets you already created. So the features and targets variable is from up here. So if you haven't run all the code, you're going to get an error there. So that's a common error students get, is like they didn't run this code recently, and then this spits out an error right now. Here, this is going to be getting the best score. So looking at the best outcome, so it's going to tell you what's your best R squared, and then the best model is going to say which outputs give you the best stuff. And then this is kind of just saying a nice way to look at the output there. So it'll be a nice little format print statement, kind of showing you like, hey, like here's your best model, here's the different, which of these combinations gave us the best one.